Hello, Ken from Intelligent Cable Design here. Today I'm going to show you a type of cable-related design that falls into the lab use, test, and integration category. It's a type of test jig that I refer to as a breakout box because it separates or breaks out the signals from a multi-signaled connector to individual connections. I've made and utilized many similar designs over the last couple of decades to support my work of testing and troubleshooting complex electronic hardware. This design utilizes a prefabricated aluminum chassis that just needs machining or drilling for component mounting. In this case, it's Hammond's 1590 series die-cast aluminum enclosures. I generally use the non-mounting flange style, unfinished, so that if I need to connect to the box for grounding and things like that, I don't have to remove any finish. And of course, it's got tons of sizes and options available. So the advantages to using these kind of boxes, well, the design is robust and fairly rugged with the internal wiring protected by the chassis. They provide for easy and reliable connections to test equipment. Connections are clearly labeled, and that will help reduce misconnections or measurement errors. The connector selections are customized during design for the intended types of test connectors you're going to want to connect to. And of course, it gives you the capability to electrically load circuits or interface to them, either continually or selectively by switching the loads on or off. And it adds a degree of consistency to measurements, as the only thing that changes between the units being tested is the unit itself. So if you had multiple boxes that you needed to test, you'd hook your test equipment up to this, and just connect this to the box you're going to test, power the box, do your tests, disconnect this, connect it to the next box, and move on. In addition to simply being test boxes, these can also be designed to be inserted between different units to monitor activity during product development or integration. They can have more complex test circuits installed, or even be designed to be connected to automated systems. When quantities were very low, like ones and twos of, I'd lay the design out in 2D drawing and just hand fabricate it by drilling out the chassis, mounting and wiring the components myself. Labeling was done manually as well, either by, Brady Labeler, Brother P-Touch, or when I had access, using a laser etcher on thin anodized aluminum plates that were trimmed to size and applied to the chassis. And then you mount the components on to keep it captive. But one program I worked on required more than 25 units, each of two very different designs. The firmware developer team members used these to develop and validate all their software programming on new hardware that was under development. So, quick peek. That's box type number 1, box type number 2. Sorry for the blurry photo. I've removed the part numbers to protect the innocent. So with those larger quantities, it became economical to design in 3D and send the chassis out to be machined or drilled for mounting the hardware and components. The setup costs for that machining were then amortized over the boxes. Thus, it only added a small premium to each individual unit's cost. So that would be a step file that you would generate after designing the location and sizes of the holes. Allows you to put some features in, like this keyway to prevent the tip jacks from rotating, the switches from rotating. Same with the B and C connectors, that sort of thing. Okay. Similarly, metallized adhesive-backed foil labels were designed, and then they were fabricated at a local graphics company and applied manually. So I'm replicating that here. There's your metallized foil label. Obviously, you allow some additional hole size around your intended holes so that when you apply it, if you're not 100% perfect, it doesn't prevent you from mounting the equipment. That's what was done here in these. This is a metallized foil label. You just peel the backs off and have the holes pre-punched, just laid it out on the chassis, and then mounted the hardware on top. So it became more of an assembly operation to apply the label to the chassis, mount all the hardware, and then wire the equipment harness into the box. It worked. Since then, I have created and implemented some improved design rules, though, in an effort to keep electrical noise at a minimum. So let's go over this example. It's based on an earlier design that I've recreated here in Fusion 360, but updated with my new design rules. This is a breakout box that connects to a common military headset connection port. Don't worry, I won't reveal any important technical details here. So, this is the equipment end connector, and it's connected to a banding adapter, providing strain relief for the cable. That adapter, banding adapter, also is used to terminate the braid shield on this cable to the adapter and in turn into the connector. And this is like I said, a shielded wiring harness here. At the other end, we have the cable grip, which provides strain relief for the cable as well, again, and also terminates the shield braid to this, which in turn electrically connects it to the chassis. So you basically have a ground circuit from, provided of course the connector on the unit is grounded, through this connector, through the back shell, through the shield, through the cable grip to the chassis, effectively making this chassis an extension of the shielded enclosure of the equipment you're testing. Okay. The chassis is also isolated from all the other connectors, the test connectors here, so that we don't have any ground loops. I'll get into that in a little bit. Actually, we'll do that now. When a single connector contact is provided by the equipment for multiple signal returns, and it's common practice, a dedicated return line for each signal is run. The returns are then common together as close to the equipment connector contact as possible to prevent mixing of the return signals on the wiring. This preserves the equipment grounding design. So what I'm saying here is, in this case, there's one pin, and it's used as the return for the ancillary DC supply, for the PTT circuit, and both the left and right ear audio signals. So what happens is, from that pin, you have a dedicated return line for the DC, a dedicated return line for the PTT, and dedicated return line for the right ear audio, and a dedicated return line for the left ear audio. So currents flowing down the wires from one signal are not mixing in this assembly until they get to the contact. And then, of course, they're mixed in the unit, but the unit's designed for that, so that's fine. Okay, in addition, this design has tip jacks here, labeled plus and minus for the ancillary DC output that a headset provides. Tip jacks, they hold standard DMM multimeter tips. So you just plug your multimeter in there. And then, of course, we've got a switch here so we can put a load on the supply. This is a 2-position switch, so we've got load on, load off. You could change it to 3-position and then have other options for loading. Dual binding posts for the balanced microphone signal. I like the binding posts. They're bigger, but they allow for multiple connection methods. You can plug banana jacks into the top. You've got through-hole wire holding, or you can use terminals, like spade terminals, plug them in and just screw down the binding posts. So multiple methods of connecting to this unit. The other nice thing with that is when you're using one for the connection, you still have a way to measure that connection, because sometimes with mic signals, they're very small, And when you hook up a function generator or a signal analyzer or anything like that, like a DSA, you may want to calibrate the signal levels when the signal is terminated on the equipment, on the mic input. So that'll allow you to measure it and adjust accordingly to get the exact signal you want. We're moving on here. Isolated BNC connectors for the ear audio outputs. These can be preloaded with required test resistances and connected to an oscilloscope or audio analyzer of some kind. An isolated BNC connector for the push-to-talk input, as well as a two-position switch to manually activate the circuit. So that activation can be like a 0 ohm dead short or some allowable maximum resistance. So it doesn't have to be two-position. You can, if you've got some other type of configuration you need, you can change that. If the breakout box travels or is shipped, you can add protective caps, captive caps to like the BNCs, the military connectors. Well, they have protective caps for that. There are things like switch guards, mini switch guards that come up and protect the toggle levers from getting banged around, stuff like that. Those can be added as well. So for designs of this nature, clients can expect a delivery package, and it'll include the following. The electronic CAD file, format step by just whichever one's desired for the machining operations if you choose to go that way and have your a shop manually a shop machine your chassis for you. And a series of PDF documents. So the mechanical drawing for the chassis itself with standard views that details the modeled information contained in the CAD file. So if, for example, the final build quantities don't justify having the machining done outside, you can use this mechanical fabrication drawing to properly locate and size the holes and modifications you need to do the chassis by hand. An art file for the metallized foil label, so you can send that out and have that done. Of course, if you don't want to, you can use another method to provide and attach individual labels, but you'll have that file. A cable assembly drawing for the wiring harness itself with embedded parts list. A mechanical assembly drawing for the entire assembly with a standard views and embedded parts list. And if it wasn't included in the mechanical assembly drawing, there'll be a separate wiring diagram to show how to terminate this wiring harness inside the box and route the wires properly. Also included in the package would be specification sheets and drawings for components used in the design. So that about wraps it up. Please feel free to comment and follow us on LinkedIn, YouTube, or visit our site at www.intcabledesign.com. Thanks for watching.